Today we are going to take a more extensive look into parabolas. So there's some key features of parabolas that we may have known before from previous math courses is that a parabola is this U-shaped graph that predominantly follows the x squared, so y equals x squared. The inverse of that being y squared equals x, so it either opens up or down, left or right. We usually have talked about the vertex being the maximum or the minimum of a parabola, and we may have looked at something known as the axis of symmetry, which goes through the vertex and cuts the parabola in half, forming two mirror images of each other. Well, as we dig that a little bit more extensively into the conic section, with hyperbolas and ellipses and even a circle, we did talk about something called a focus or a foci. We had 2 points most of the time that were called foci, and they were equidistant from the center. And when we were looking at circles, the foci were actually the same point, which also lied at the center of the circle. When we're looking at parabolas, we also have a focus, which is one point that lies, I describe it as inside of the parabola. It is within that um, parabola's space. So like in this section right here, your focus will lie within that shaded area of your parabola. But like ellipses and hyperbolas, we had 2 foci, and they were equidistant from the vertice or from the center. With a parabola, you also have another key feature that is equidistant from the vertex, opposite of the focus, which is called this directrix. So it is this line that we use to create our parabola. So our parabola is actually the any point on your parabola is going to be, let's say this point up here. This point anywhere on your parabola, anywhere, is going to be exactly the same distance from the focus as it is from your directrix. So it's this just relationship between the focus and the directrix is what creates the shape of the parabola and why it functions the way that it does. Our focus, when we were looking at ellipses and hyperbolas, we were dealing with distance in terms of c. So c squared equals a squared plus or minus b squared. With a parabola, our focus is going to be represented by the variable p, and p represents nothing more than a distance, a measurement from the vertex, which I also refer to as the center, just kind of keeping vocabulary consistent. So if you hear me say vertex or you hear me say center, know that I'm talking about the same thing. So some key features. Another key feature that's brand new is this concept of something called a latus rectum. So the latus rectum is the distance from the focus directly to your parabola. So we say endpoints of the latus rectum. It represents how wide or how narrow your parabola is along that focus. So the relationship between the focus and, let's say, the vertex, or if it's, very wide, if it's going to be a wide parabola or if it's going to be a narrow parabola. The larger the latus rectum, the wider your parabola. The smaller your latus rectum, the narrower your parabola. And that latus rectum is going to be from the focus to the endpoint. So from the focus to the parabola is going to be twice the distance as from the focus to the vertex. So remember that the distance was represented by the variable p. So from the vertex to the focus, let me highlight that. From the vertex to the focus, here. So from the vertex to the focus is p units. the latus rectum measures from the focus to the endpoint, a value of 2p. So from the vertex to the focus is p units. From the focus to the edge of the parabola is two units. And it does travel both left and right, or up and down, depending on how your parabola opens. So in this case, we're going to travel left to right. And it is 2p units on the left, 2p units on the right, or it has a total distance of 4p, which is also going to be quite visible in your equation. So that value will be given to you, and then you can find your p-value from there. And so a lot of information in regards to parabolas and kind of the new key features that we're looking at. I have combined information into one table. So we have two cases of a parabola. We have parabolas that open left and right. Those parabolas might look something like this. So let me get just a little sketch here. It could open to the left, or it could open to the right. And these are represented by the equation y minus k squared is equal to that 4p value, that latus rectum, times x minus h, with your center or your vertex being located at hk. Your axis of symmetry, depending on if it's left to right, your axis of symmetry will be some sort of horizontal line through your vertex. Whereas if you are opening, let's say up or down, so here's up and here's down, then your axis of symmetry is a vertical line that passes through your vertex, which is where we come up with y equals k if it's horizontal, or r x equals h if it's vertical. Your equations also look very similar, with the exception of who is squared. So if my equation opens left to right, my y value is squared and my x is not. If my equation, if my x is squared, it opens up and down, but my y is not. Your focus, now from here on down, it looks really scary because there's a lot of variables that are happening. Each one represents something different. But your focus, remember, just like from the ellipse and from the hyperbola, is a distance from the center. In a parabola, that center is called your vertex. So if my graph opens to the left or to the right, then my focus, let me zoom into some of my examples here. If my graph opens to the left or to the right, then my focus is going to be inside of that parabola. So if you're moving to the left, you subtract your distance from your vertex. If you're moving to the right, you add your distance to the vertex. So it travels in the correct direction along your x-axis, which is why we come up with that equation h plus p k. So you're taking your h value from your center and you're adding your p. And then if your p value was negative, then obviously you'd be moving to the left because you'd be adding a negative number. But the formulas don't matter if you can understand the concept, because then you're like, okay, the formula will make sense once you can kind of understand that focus is just simply a distance from the center. So you're going to add it. If you're moving, if it opens left or right, obviously your center is going to be left or right of your vertex. So you're going to be moving your x value from your center. If it opens up or down, then you're moving up or down from your vertex. So you're changing your y value of your focus. The directrix, again, is just that line that's the same distance away from your vertex as your focus, but just in the opposite direction. So we're just going to take our axis of symmetry, or our, not your axis of symmetry. You're going to take your x or y coordinate from your center, and you're just going to adjust it to that value of p. And then your lotus rectum points, again, are the distance from the focus, 2p units. away depending if it moves up or down. If it moves up or down, then your latus rectum moves left and right. So it kind of moves in the opposite direction of how it opens. If your parabola opens left to right, then your latus rectum moves up and down. So here is a chart that kind of maps out all of the information. It can feel extremely overwhelming, but we are going to do two examples where we break it down, put it into practice, and I think when we actually see it in action, the vocabulary is a little intimidating, but the process isn't too complicated. Our first example, and we're supposed to graph this parabola. Now, if we were in a lower level math course, we would just simply plug in some x and y values. You can find your vertex, you can put it in Desmos, you can graph it, but we want to graph it with all of its key features. So that focus, the directrix, the axis of symmetry, your latus rectum. And we're going to start by reading our equation and kind of inferring some information. So identifying things that are absolutely true and then maneuvering through the equation to find all of our missing key features. We've got the parabola x minus 4 squared is equal to 28y minus 8. I'm going to graph it, but I'm going to graph it with all of its key features. So just like last time, I need to have some sort of direction, some sort of bearings on this parabola in order to navigate it correctly. So I look for my square value. My square value deals with the x component. So this lets me know that I'm either moving upwards or downwards. My parabola will either open up or down. So if I have one that opens upwards, it's going to look like a happy face. If it opens downwards, it looks like a sad face. And some important information that we can kind of conclude from that is that your axis of symmetry is a vertical line passing through your focus and your vertex. Your lattice rectum will be a horizontal distance traveling from your focus to the edges of your parabola. And that lets me know that my focus is either above or below my vertex. So that lets me know which coordinate of my vertex needs to be manipulated. So going through my equation, I know that the center of my parabola or the vertex is located at 4, 8. I also have a total lattice rectum distance of 28. So that will always be provided for you, and that is that value right there. Now that 28 is equal to 4p, which means that if I divide both of those by 4, I have a p-value of 7. So my p-value is positive, meaning that my graph will open upwards, and my focus is going to be above my center. So if I take my center, my center is located at 4, 8. I can move my y component up 7 units, and I now have a focus located at the ordered pair 4, 15. So let me graph those 2 points. My graph is small, so I am going to count by 2s. So 2, 4, 2, 4, 6, 8. Here's my center and my focus, 10, 12, 14, 15. If my focus is 7 units above my vertex, then my directrix is 7 units below. So 2, 4, 6, 7. So I have a directrix that is at the line y equals 1, which means that I also have my axis of symmetry that's going to pass through my focus, through my vertex, is perpendicular to my directrix, and that is at the line x is equal to 4. So from here, I have my vertex, which is the center of my parabola. I have my focus, which is a distance, and now I can find my endpoints. So I need to move equidistant to the left and to the right of my focus. So my lattice rectum endpoints are going to be 2p units from the focus. So I've got those absolute value bars. So 2 times 7. So I have endpoints that are going to lie 14 units away from my focus. Since my graph opens up and down, then I know that my lattice rectum is going to run left to right, so it's going to run opposite. So I'm going to take my focus is at 4, 15, and I'm going to move it to the left, and I'm going to move it to the right. So I'm going to use my ordered pair to do that calculation. So my left and right movement is controlled by my x coordinate. So I can take my x coordinate and move to the left 14 units. And I can take my x component and move to the right 14 units. So keeping your thoughts all organized. So that means that I have endpoints at -10, 15. So that's one endpoint, and the other endpoint is at 18, 15. So if I was to come back up here and graph those, I would have an endpoint at 2, 4, 6, 8, 10. So -10, 15. And 18, oops, I've got that on the wrong, it's 2, 4, 6, 8, 10, and there's my 15, and 18, 15. And those points physically lie on your parabola, and so now you have enough to sketch out a really rough graph here. Oops, we'll just go from the vertex. So you have, if I was to go back and look, I have a lattice rectum distance here from endpoint to endpoint through the focus that is exactly 28 units long, just like from my equation. I have a vertex that's located at the point 4, 8, a focus that's located at the point 4, 15 because it's 7 units away. My directrix is located 7 units below my vertex. And then my lattice rectum is each one of those endpoints is exactly 2p away from the focus. So p being 7, so they're both 14 units to the left, 14 units to the right, giving me a total distance of 28.